Swayam Prabha. Digital India. Educated India.
Hello everybody, today I will start the module 4. So, first lecture I am starting with a topic that covers the plate equation in polar coordinate system. So far we have introduced you and solved some problems of rectangular plates and other plates also of some special cases like circular plate or elliptical plate and triangular plate also. Now, it will be advantageous when we use the plate equation for some specific problem where the axial symmetry is there. For example, circular plate loaded symmetrically and boundary condition is also symmetric with respect to an axis of rotation passing through the center of the plate, then it is possible to find the solution of the system equation in the polar coordinate system. So, today our discussion will be governing differential equation of the plate in polar coordinate system and introduction to axisymmetrical bending of the circular plate. So, specifically we will use the polar coordinate system to circular plate problem. Okay. So, today I want to cover the following topics: transformation of equation of bending of plate from Cartesian coordinate system to polar coordinate system, then axisymmetrical bending of circular plate in polar coordinate system, then derivation of displacement, strain relations, stresses and bending moments. So, this expression how it changes, because we are familiar with the rectangular coordinate system, the bending moment expression for plate or shear force expression for plate and stresses also we could find. But now, let us see how this relationship will change when we carry out the transformation of the coordinate system. Then we will derive specifically for axisymmetrical bending of circular plate the equations of equilibrium for a element, infinitesimal element, and from that we get the differential equation for the bending of circular plate with axisymmetrical condition. Now, after getting this equilibrium equation, we can proceed to solve several problems encountered in practice, because most of the problem in circular plate comes with a axisymmetrical loading or axisymmetrical conditions of boundary and loading. Then we can find the deflection equation and bending moment, shear force for that type of boundary condition and the loading condition for a circular plate, and make use of these results for designing of the plate element or slab which is modeled as a plate. So, these are the topics that I want to cover today in today's lecture. So, let us see first how this system equation or the plate equation can be transformed into from rectangular coordinate system to polar coordinate system. So, you know very well that polar coordinate system is expressed in terms of two variables, the radial distance of the point from the origin r and the angle that the radial line makes with the reference axis. Here we take the x axis. So, the point p x y in Cartesian coordinate system will be transformed to a point p with coordinates r and theta, where r you can easily you can see that x coordinate equal to r cos theta and y coordinate is equal to r sin theta. And you can also see that tan theta will be y by x. Okay. So, with that relationship x and x is equal to r cos theta, y is equal to r sin theta, we will be able to transform the equations of bending of plate derived in the rectangular coordinate system like del 4 w x y equal to q x y by d, where d is the flexural rigidity of the plate. It is nothing but equal to E h cube divided by 12 into 1 minus mu square, where mu is the Poisson ratio of the plate. Okay. So, plate equation now can be written like this also. Say del square is the operator, Laplacian operator is very well known to the students of the mechanics or physics. So, del square equal to del square by del x square plus del square by del y square. This is the Laplacian operator in differential calculus, and del square w x y, again we operate on w. So, plate equation can be written in this form del square into del square w x y equal to q x y by d. Okay. Now, our intention is to change the Laplacian operator in the polar coordinate system. So, the equation of the plate in transform form can be written as del r square operated on del r square w, where w is a function of r theta and q is also function of r theta. D remains same, whether you change the system of coordinate, it will not differ. Now, here you can see that w and q, which was previously the functions of x and y, now it becomes functions of r and theta. Okay. So, you can see that now our intention is to, or aim will be to transform the Laplacian operator, that is del square, into the polar form del r square. So, you can see that del square contains the operator del square by del x square and del square by del y square. That means, second derivative of this quantity. So, first let us transfer this or transform this, the del square Laplacian operator in rectangular system to polar coordinate system. Then we will be able to write the equation in polar coordinate system. Okay. In polar coordinate system, w r theta and q r theta are functions of r and theta and giving the deflected surface and loading respectively. So, it depends both quantity r and theta, but for axisymmetrical cases where it has the plate possess rotational symmetry, then the w and q will be only functions of r. So, they will not depend on the theta. So, to transform the Laplacian operator in rectangular coordinate to polar coordinate system, let us find the write the derivative del w by del x using the chain rule, introducing the variable r. So, del w by del x can be written as del w by del r into del r by del x plus del w by del theta by del x. Okay. Now, if we look back to equation 1, equation 1 is this x is equal to r cos theta and y is equal to r sin theta. So, you can find a relation between r with x and y. So, r square is equal to x square plus y square. So, that relation we will be using here. So, x square plus y square is equal to r square, that is found because x is expressed as r sin theta and y is expressed as r cos theta. So, when x is squared and y is squared and both are added, you will get r square. Okay. Now, in order to find out this del r by del x, let us differentiate this quantity with respect to x. So, if you differentiate this with respect to x, you will get for this you will get 2x, and here because this is not containing any x. So, differentiation of y square with respect to x will be 0. So, 2x equal to 2r into this dr by dx, because first we are differentiating with respect to r, then we are introducing this variable dr by dx. Okay. Now, dr by dx is now x, and x is, you know that it is cos theta. So, we got this quantity. Okay. Similarly, when we want to find this d theta by dx, now let us see what is theta. Tan theta is equal to y by x. So, theta will be tan inverse of y by x. So, differentiation of function, inverse function is given by that, say u is a tan inverse u is a function, inverse trigonometrical function. So, its differentiation with respect to variable u will be 1 upon 1 plus u square. Now, here u is y by x. So, substituting this, you will get that del theta by del x equal to minus y by x square plus y square, and you know that x square by y square is equal to r square, and y, you know that y is equal to r sin theta. So, naturally it will be del theta by del x will be minus 1 upon r sin theta. So, these two quantities we got in this equation. Now, we substitute this del w by del x cos theta del w by del r and minus 1 by r sin theta del w by del theta. So, first derivative is obtained. So, this task is completed. Now, let us go to the second derivative, because to find out the Laplacian operator we must get the second derivative, then we can isolate the operator. Okay. In the second derivative of this w, we got this already. So, this operator del by del x is cos theta into del by del r minus 1 by r sin theta del by del theta. So, you can see this operator I have written, I have isolated this operator, differential operator and other variables. So, w is isolated, separated. Now, to take the second derivative of that del w by del x, we write del square w by del x square equal to del by del x, that is differentiation of del w by del x again with respect to x, to find out the second derivative. Now, here you can see that d by dx, that is the operator, we have already found out. So, we write here this operator cos theta del by del r minus 1 by r sin theta del by del theta. Then del w by del x, we already found it here. So, we write here again del w by del x, that quantity will be cos theta del w by del r minus 1 by r sin theta del w by del theta. So, this is actually, this quantity is del w by del x. So, this is quantity is this. Okay. So, after operating this with this operator, this function, then you will get del square w by del x square equal to cos square theta into del square w del r square plus 1 upon r square sin square theta del square w del theta square plus 1 by r sin square theta del w by del r minus 1 by r sin 2 theta del square w by del r del theta plus 1 by r square sin 2 theta del w by del theta. Now, you can note here I have used different colors for different terms. So, I will explain what is the significance of that. So, you can see the second derivative of w is now expressed in terms of variable r and theta. Okay. So, similarly, one can obtain this del w by del y, that using the chain rule of differentiation, del w by del y can be written del w by del r by del w, del r by del y plus del w by del theta by del y. So, this is the expression of del w by del y using the chain rule. Okay. Now, already we know that del r by del y equal to sin theta, that we can prove it, because if we go to the first expression, this expression, then differentiating again with respect to y, you will get this 2y here, and here you will get 2r del r by del y. So, you can find del r by del y equal to y, and y we know that in polar coordinate system y is r sin theta, r will get cancelled. Okay. So, then del theta by del y you will get again in this similar fashion 1 by r cos theta. Okay. So, now this expression can be written as del w by del y equal to del w by del r into sin theta plus del w by del theta 1 upon r into cos theta. Okay. So, this expression is written like that. Now, on further differentiation, as we know, as we have done earlier, that means we can now separate the operator del w by del y, and we can write that operator del w del by del y, this is the operator, differential operator, equal to sin theta del by del r plus 1 by r cos theta del by del theta. So, then differentiation of del w by del y again with respect to y will yield the equation like that. So, here you can see I have also used the different colors for different terms. Previously also in the equation 5 I have used different colors for different terms. Now, here you can see, if I see the red color term cos square theta into del square w by del r square. So, let us take the first term of this first term of this Laplacian equation, that is del square w by del x square, very popular equation. So, del square w by del x square in the polar form, there are say 1, 2, 3, 4, 5 terms. So, let us take the first term which is marked with the red color. So, cos square theta del square w by del r square in the equation 5. Now, we go to the equation 7. Equation 7 we have got sin square theta del square w del r square. So, this is also red color term. So, if I add this, because our intention is to find the Laplacian operator in polar coordinate, that is transforming the Laplacian operator from rectangular coordinate to polar coordinate to find out the equation of the plate. So, if I add equation 5 and 7, you see the addition of the red term here and red term here will yield you this del square w by del r square multiplied by cos square theta plus sin square theta. So, this is 1. So, after adding you will get first term as del square w del r square, that is sure. Now, let us come to the second term. This second term of the equation 5, there is 1 upon r square sin square theta del square w del theta square. You can see del square w del theta square, and with that coefficient is 1 by r square sin square theta. So, this is written as a with the green color in this equation 5. Similar term we will find in the equation number 7 with the green color. Okay. Now, if I add, again you are finding that common term is there in both the equation del square w del theta square into 1 upon r square. So, naturally if I take common 1 upon r square del square w by del theta square, and then the term these other terms in the parenthesis will be cos square theta plus sin square theta. So, naturally the another term in the polar system will be 1 upon r square del square w del theta square. Okay. So, originally you have seen there are 5 terms, but here you can see that only 3 terms are there, that means other terms will get cancelled. Okay. So, if I now see this term 1 upon r sin square theta del w by del r, here it is blue colored, equation number 5. Equation number 7, let us see, equation number 7 also it is blue color, and the coefficients is with cos square theta. So, naturally when it is added, then it will be 1 upon r dw by del r. So, the other terms, the 1 upon r sin 2 theta del square w del r by del r del theta minus 1 upon r square sin 2 theta del w by del theta have alternate signs. So, they will get cancelled, equal but opposite signs. So, they will get cancelled. So, after transformation we will get the Laplacian operator in polar coordinate system to be consisting of 3 terms del square w del r square plus 1 by r square del square w by del theta square plus 1 upon r del w by del r. So, our one of the important task is over now, because to find the plate equation, fourth order plate equation, we need the Laplacian operator, then we will operate again with the equation del square w. Okay. So, this term, this operator or this differentiation or the addition of these two curvature have been already carried out and we have converted to the polar system. Okay. Now, we can conveniently write del square r equal to del square by del r square plus 1 upon r square del square theta del theta square plus 1 by r del by del r. So, this is the Laplacian operator in the polar coordinate system. Okay. Now, we know the general expression of moments and shear that can be written now in this form m r equal to minus d bracket multiplication with the terms del square w del r square plus mu into 1 by r square del square w del theta square plus 1 upon r del w by del r. So, this is equation 10. Then the m theta, the bending moment in the circumferential direction, m r is the bending moment in the radial direction. So, m theta is the bending moment in the circumferential direction is 1 upon r del w by del r plus 1 by r square del square w by del theta square plus mu into del square w del r square. This can also be found because the bending moment expression contains the second derivative of the quantities. So, second derivative we convert, now we have converted into polar coordinate system and using this we can find this expression, that is equivalent expression in the polar coordinate system. So, the stress resultant, that is we consider in the circular plate or in the polar coordinate system are m r the radial moment, m theta is the circumferential moment and m r theta is the twisting moment. Okay. M r theta is the twisting moment, q r is the shearing force and q in the direction along the arc and q theta is the shearing force along the orthogonal in another perpendicular direction. So, that means q r and q theta, these are the shear forces that is present in case of plates of circular shape or any other but when the polar coordinate system is used. Interestingly, you will find that for axisymmetrical problem the quantity will be only dependent on r. So, anything which is involving the theta, that is dependent on theta, should be dropped, that is w in case of axisymmetrical problem will be only a function of r. So, this term does not come into picture when we consider the axisymmetrical condition. So, that will come later, but now you have understood that transformation of Laplacian operator from rectangular coordinate system to the polar coordinate system. Okay. So, the twisting moment m r theta r is also written as minus 1 minus mu into d. D is the flexural rigidity of the plate, which is the same quantity as we have found in the rectangular plate. D has no relation with the change of coordinate system, into the derivative, partial derivative with respect to r, then derivative r of the function 1 by r del w by del theta. Okay. Then shearing force q r equal to minus d del by del r, and this is the Laplacian operator in polar coordinate system consisting of three terms. Laplacian operator in rectangular coordinate system consists of only two terms, but Laplacian operator in polar coordinate system for general condition when these quantities are dependent on r and theta contains three terms. Okay. So, q theta is also written as minus d 1 upon r del by del theta del r square w. Del r square is introduced to you, I have given the detailed derivation of del r square. Okay. Kirchhoff's S shear, that is at the free edge or at the other edge where the twisting moment, shear force as well as bending moment, three quantities are there, but it is seen that the three forces are not necessary actually. Three quantities are not necessary for expressing the boundary condition, because the twisting moment has contribution to the shearing force So, that have been pointed out by these previous authors, and Kirchhoff has modified the equation of S shear, that is the shear force along the edge. He has expressed as V r equal to Q r plus 1 upon r del r m r theta by del theta. So, this is the quantity where the m r theta or m theta r has to be substituted from this quantity and Q r has to be substituted from here. So, ultimately you will get the S shear force, radial S shear force equal to minus d and this del by del r square. Del r square is the Laplacian operator in polar system W plus 1 minus mu divided by r del by del theta bracket 1 upon r del square W del r del theta minus 1 by r square del W by del theta. You can note here that this term del r by del theta is due to contribution of m r theta in the S shear. So, that you have noted, and this V r is written like that. Similarly, the other S shear, that is V theta, can be written as Q theta plus del m r theta by del r. After substituting Q theta as minus d 1 upon r del by del theta del r square W and m r theta equal to m theta r equal to minus 1 minus mu into d del by del r 1 by r del W by del theta in the above expression. Okay, in the above expression we get this quantity after simplification. So, this is a very large equation, and sometimes if the boundary condition is such that we have to impose V theta, then we have to use this equation minus d 1 upon r del by del theta del r square W plus 1 minus mu del by del r bracket 1 upon r del square W by del r del theta minus 1 upon r square del W by del r. Okay. So, the expression for the radial moment, circumferential this moment, then shear forces Q r Q theta and the Kirchhoff's S shear V r V theta are given to you. Okay. Now, let us see what will be the change in differential equation. Okay. So, differential equation originally was del square operated on del square W equal to Q by d, where del square was the Laplacian operator in rectangular coordinate system. But we have now known this transformation of Laplacian coordinator in rectangular system to polar coordinate system. So, we can now write this plate equation in polar coordinate system as del r square into del r square W, that is del r square is the operator which consisting of these three terms del square by del r square plus 1 by r square del square by del theta square plus 1 upon r del by del r. So, when it is operated with this function del square W, then we get the full plate equation. So, you can write this thing in this form after getting, and then after operating you will get the fourth order differential equation of the plate. Okay. Now, let us derive the condition for axisymmetrical loading and boundary conditions. Okay. Because the plate equation that originally contains the W as a functions of r and theta, and Q is also a function of r and theta, involves the fourth order differential equation, partial differential equation. Okay. Now, for axial symmetry, for a circular plate under the action of lateral load which are rotationally symmetric. Rotationally symmetric means that is the only a functions of, that is the stress, deflection or loading, anything you take, all will be dependent on r at any direction or at any orientation theta, there will be no change. So, that condition is known as axisymmetrical condition. For example, a circular plate which may be simply supported at the edges or may be clamped or may be similar kind of is in the same edge condition and it is continuous along the boundary. Okay. So, in that case we can call that the plate is having the axisymmetric condition, and then there is a deflection, and this q which will be q, that is the load that is applied on the plate, will only be a function of r. There is, for example, you take a circular plate and it is uniformly loaded. So, at any radial distance you will get the load is q, that is the uniformly distributed load intensity. Now, if you take say another condition, say circular plate, and it is loaded with a linearly varying load gradually increasing from 0 to maximum at the edges linearly. In that case also, at any radial distance you will get this same load intensity. So, that means it also falls under the category of axisymmetrical condition. So, in the axisymmetrical condition, W will be W r theta, which is actually the function dependent variable of the functions, then it will be converted to only W r, and Q r theta, r and theta are the dependent variables of the function. So, it will be converted to Q r. Okay. So, with this simplification, now we can very easily see that this operator has no meaning, because del square by del theta square will go to 0. Okay. Del square by del theta square will be equal to 0, because this derivative does not exist, because it will be a function of r only, anything. So, this will remain, and here this quantity will remain. This will have no significance, because del square W del theta square again will be 0, because W will be only function of r. So, this quantity will remain, and Q will be only function of r. So, instead of partial derivative, now we can write it as a ordinary derivative differential equation. So, partial differential equation is not necessary here, we will get the ordinary differential equation. So, therefore, the Laplacian operator reduces to only two terms here, del square by del r square plus 1 upon r d by dr, and then this is the quantity that we get, and equal to q r by d. So, this is very simplified situation, and most of the cases this situation exists in practical field. So, we take this differential equation of the plate to find out the deflection and other stress resultant. Okay. Now, let us see what are the quantities that we have to take into account. We have to take into account this bending moment in the radial direction and bending moment in the circumferential direction, and due to axisymmetrical condition, the q theta and m r theta will be 0, only q r will be existing. Okay. Now, say this is a portion of a plate, okay, of very small length d r at a radial distance r, and which subtends an angle d theta, and q is the transverse load acting on the plate. So, you can see at any element of the plate, the stresses in the radial direction is sigma r. So, force on the element will be sigma r dA, where dA is the this area of the plate, and the shear stress that is acting along the edges will be 0, because in axisymmetrical condition there will be no shear stress, but vertical shear stress will exist, and vertical shear stress is on this tau r z, and it will have a parabolic distribution, and it is neglected in our thin plate theory. So, in axisymmetrical condition, tau r theta is not to be considered, only the stresses, that is sigma r and sigma theta, are of importance. H is the thickness of the plate. So, this is demonstrated here. The stress distribution will be linear, but we will prove it later on with the expression. Okay. Now, let us see an element of the plate of width dr that is shown in the band configuration. Okay. So, you can see that the slope of the plate is del dw by dr. So, due to deflection of the plate, it will undergo the displacement along the radial direction, and that displacement is u. Here it is shown u here. Now, since it is the negative direction of the r axis, because here the axis are the important direction is r here in the radial direction, and w is your this the vertical displacement, and u is the radial displacement. Okay. So, you can see that u, that is the this axial displacement or radial displacement we can call, can be expressed in terms of, if this point is located at a height z and this slope is same as this slope del w by del r, then it can be expressed as z dw by dr. So, this height into tan theta, and because of small deflection we take the tan theta, that is theta is dw by dr equal to theta, that is dw by dr, tan theta is equal to theta. Okay. The negative sign is taken because u is measured in the negative direction of the this axis r. Okay. So, the strain u is now minus z dw by dr. Okay. Now, let us take the slope phi equal to dw by dr, or you can call it theta also, any angular symbol you can give here. So, u is minus z dw by dr, that is the displacement in the radial direction. So, naturally the strain in the radial direction will be epsilon r equal to the derivative of u with respect to r. So, if this is known, u is known, then it will have the strain in the radial direction is minus z del square d square w dr square. So, strain in the radial direction is known. Okay. Strain in the circumferential direction now can be obtained like that, because of displacement u in the radial direction, the radius changes from originally it was r, now it will be u plus r. So, the change of the circumferential length will be 2 pi u plus r minus 2 pi r. Change in length divided by the original length will give you the strain in the circumferential direction. So, you can see from this quantity the strain in the circumferential direction is nothing but u by r. So, after obtaining the strain in the radial and circumferential direction, we can now express the stresses using the Hooke's law. So, because we are dealing with the linear elasticity, so we will use the Hooke's law. So, using the Hooke's law, the sigma r equal to E divided by 1 minus mu square into epsilon r plus epsilon theta. Epsilon r, epsilon theta are the strains in the radial and circumferential direction. Similarly, sigma theta, that is the strain in the circumferential direction, is written as E divided by 1 minus mu square into E theta plus epsilon theta plus epsilon r. Epsilon is used to denote the strains, which are actually small quantity. So, knowing the strains, and we already know the quantity epsilon r, now we can express sigma r sigma theta in terms of the distance from the middle surface, because middle surface is our reference plane. From the distance measured from the neutral surface, positive upward and negative downward, then we can express sigma r equal to minus E z. E is the modulus of elasticity of the material of the plate, divided by 1 minus mu square into del square w del r square nu by r dw by del r d square w dr square, because here only the total derivative is of importance, because the partial derivative has no meaning here, because this w is a function of only one variable. So, similarly, sigma theta, that is the stress in the circumferential direction, can be written as minus E z divided by 1 minus mu square bracket 1 by r dw by dr plus mu into d square w dr square. You can note here that in the stress expression of in the radial direction or circumferential direction, whatever you call it, both quantities, say slope as well as curvature, both are involved. So, slope has contribution in the stress, and also the curvature has also contribution towards the stress. So, this is the expression, these are the expression for the stresses in the radial and circumferential direction. From this expression 19, one can note that sigma r and sigma theta varies linearly with z. So, the variation here is shown in the above the neutral axis, this is the middle surface, it will be compressive, and below the middle surface it will be tensile. Similarly, this sigma theta variation on the other edges, it is shown like that, a linear variation, and tau r theta is 0, but tau r z will exist, it will have a parabolic variation, but its value is negligible and we will not consider in the deriving the plate equation. Okay. So, we have already obtained the differential equation of the bending of plates, circular plate under axisymmetrical condition. So, this equation is valid. You can directly now use this equation to solve the axisymmetrical problem of circular plate. But here I will demonstrate also the derivation of the differential equation by using the force balance, that using the concept of mechanics. Previously I just used the calculus to transform the differential equation in this rectangular system to polar coordinate system. Now I intend to do with the help of the principle of mechanics. So, before that, let us find the expression for radial moment and circumferential moment. Okay. So, radial stresses we have obtained sigma r, and on the small element dA, the force is sigma r dA. What is dA? The element is taken of width 1 and the depth is dz. So, dz into 1 is the area of the element. So, force into distance about the neutral axis will give the moment, and if it is moment on the element, force acting on the element, after integrating along the depth of the plate minus h by 2 to plus h by 2, we get the moment radial direction, which varies this radial moment, full radial moment, complete radial moment, taking the contribution of all the elements, differential element. So, m r after integration is converted to like that, E by 1 minus mu square del square w del r square mu into r d w by del d r. Here only the ordinary differential coefficient is taken. So, there is no necessity to use the partial derivative sign. Okay. Then z square dz, it is integrated in the limit minus h by 2 to plus h by 2. After integration and after cancelling some term or arranging some term, it will be converted in this form, minus E h cube divided by 1 minus mu square, and inside the bracket the curvature d square w divided by d r square plus mu by r d w by d r. So, this quantity you can see the constant E h cube divided by 1 minus mu square is same as the parameter that we have found in case of rectangular plate. This is called the flexural rigidity of the plate. So, there is no difference in the flexural rigidity of the plate, because it depends on the this thickness of the plate as well as the material properties. Okay. Similarly, that you can write it after denoting this E h cube divided by 1 minus mu square with the symbol d. Okay. Similarly, the circumferential moment m theta can be found in the circumferential direction. If I take a element, then with the similar procedure I can calculate this or find an expression for m theta after substituting the value of or the expression for sigma theta. So, then m theta becomes minus d into 1 by r d w by d r plus mu into d square w by d r square. So, these are the expression for bending moment in the radial direction as well as circumferential direction. Okay. Now, equations of equilibrium of the plate under axisymmetrical condition. So, let us consider a portion of the circular plate and the forces acting on the elements or the moments acting on the elements are shown. This is q r. On the opposite edges it is q r plus d q r. D q r has to be understood as this, the differential incremental term d q r by d r into d r. Okay. Then m r, an incremental term is d m r, which has to be understood as this d m r by d r into d r. Okay. So, this I have in the short form I have written here. So, in the circumferential direction m theta and along the other direction for keeping the equilibrium it is m theta. So, m theta will remain same, there will be no increment along the circumferential direction. Okay. So, consider this sectorial element of the plate, the thickness of the plate is h. The equilibrium condition is considered. First, let us consider the force equilibrium. So, force equilibrium in this z direction, that is the vertical direction if I call it. Then the length of this element is, if this length is r, then r d theta is the length of the element. So, r d theta or d phi whatever you call, this is the differential angle. So, q r r d theta is the force along this edge, vertical force. On the other edge, this is q r plus d q r by d r into d r by d r into d phi. Okay. So, this edge length is increased because this radius, this radial distance is r plus d r. So, the area the length is r plus d r d phi. Okay. So, this you can note it. So, these two forces we have written, and then the transverse load, the vertical load that is acting on the surface of the plate is q per unit area. So, total area of this element that is colored here is q into d r into r d phi. So, q into d r into r d phi. So, this is the total force on the element. So, equating to 0 and then getting this simplifying this, that first I carried out term by term multiplication, and then you can get this many terms are common, that can be, and many terms and some terms are having a product of a square of small quantity d r. So, taking this advantage, that is cancelling common terms and ignoring the term with the square of small quantity, then we can write the equation in this form. Okay. After dividing both sides by d r d phi. So, both sides are divided by r d phi or r d phi, and then this we get this equation in this form. Okay. So, q r d r d phi equal to minus q r d r d phi. Okay. Neglecting the square of the small term. Now, carrying out integration over the domain of the plate. Now, let us integrate it. So, domain of the plate is for radius at any radial distance r, the radial distance varies from 0 to r. So, 0 to r is the limit for radius, and angle after full rotation, because it is axisymmetrical condition. So, full rotation has to be there. So, 0 to 2 pi. So, we carrying out integration of the both sides, we get here 2 pi r into q r equal to minus 2 pi 0 to r q r d r. Okay. And then from that quantity we can write q r is equal to minus 1 by r q r d r. So, this is one equation. Okay. Then second equation is considered after taking the moment equilibrium. We consider moment equilibrium in radial direction. Okay. So, if I take the moment equilibrium in radial direction, in this side this is m r, and total moment along this side is m r r d phi, because all the quantities are expressed in terms of quantity per unit length. So, m r, m theta etcetera, q r or q theta whatever may be, these will be in terms of the parameter or quantity per unit length. So, therefore, to get the total force or moment, we have to multiply it by corresponding length. So, m r into r d theta is total moment along this edge, and along this edge you will get m r plus d m r by d r into d r, and this length, the arc length r plus d r d theta. So, the moment of all the forces are taken. This is first we take the moment, and then the you can note here that in this side the force is upward q r, on the other side q r d q r. Okay. So, we take q r r d theta d r because this term is small. So, we can take these two forces, that q r and q r, which are equal and opposite in nature. So, it produces a couple. So, we take the advantage of this small distance or small value of d q r. Therefore, we have stated that q r r d theta d r, this quantity is the equivalent couple after neglecting the small difference between the shearing force on two opposite edges of the element. Further, you can see that this term is coming. How this term is coming? If you see m theta here, m theta, and m theta, if you see this, if you use the right hand rule, then it will be a vector which is pointing towards the center, okay, towards the center. Then in this side, if you consider m theta and use the right hand rule, then you will see that this is a vector which is away from the center. And if you resolve it in the radial direction at the center, then d theta by 2, d theta by 2 will be there, and this it will be your this m theta cos d theta by 2, and here also m theta cos d theta by 2. Since d theta is small quantity, so we can see, we can take it that cos d theta is equal to 1. Now, since both the vectors, though it is pointing, if you use the vector notation for the moment, and it is pointing towards the center and another is pointing away from the center, but the effect is same, both the moments are symmetrical and it is causing a sag in the plate. Okay. So, therefore, this is added, the components are added, and we have written m theta d r d theta as the another term in the equilibrium equation. Further, m theta d r d theta is the sum of the component of the moment vector m theta along the radial direction. So, that quantity we have taken, and another thing is that when we take the moment of the external load about any edge, so this length is d r. So, d r by 2, because the total load again d r is coming when you compute the area, and distance also d r by 2 will come. So, this d r into d r square will appear in the moment expression, then we neglect it because it will be a small quantity, and it is not necessary to increase with the terms which has no significance. Okay. So, simplifying this, we write this m r d r d theta minus d m r by d r into r d r d theta plus m theta d r d theta minus q r r d theta d r equal to 0. Dividing both sides by d r d theta, we ultimately get this quantity m r plus d m r by d r into r minus m theta plus q r into r. So, q subscript r indicates this radial shear along the edges equal to 0. Now, the expression for m theta is this, and expression for m r also we know. Expression for m theta is this, and expression for m r is this. So, this is the expression for m theta and this is the expression for m r. So, after substituting this expression, and then we can write this m r equal to minus d. Again this m r is differentiated. So, this differential coefficient is written d by d r, and d is there, capital D is there, flexural rigidity, r is there. M theta we have expressed, this is the expression for m theta, and then plus q r into r. So, this is written, and now to simplify the equation, let us take this symbol, the slope as xi, angle xi. So, substituting this slope here dw by dr as xi, we can now express the quantity d xi by dr plus nu into r into xi, here dr d by dr, and then the curvature is derivative of the slope, like that we have written, plus nu into r into xi plus d bracket nu into d xi by dr plus 1 by r xi plus q r into r equal to 0. So, here what we do actually, we now differentiate this and after term by term differentiation we get this quantity inside the bracket, because this is a product of two function 1 by r into xi, which are both are functions of r. So, it is differentiated and we get one more term here after differentiation. Previously it was 2 terms, now we get 3 terms, because after differentiation with respect to r it will be d square xi by dr square, and then after differentiation with respect to r, this variable xi, then it will be d xi by dr, then 1 by r has to be differentiated again. So, this is differentiated and it is written, this quantity is written plus a q r into r equal to 0. Dividing throughout by dr and rewriting after cancelling some common terms, you will get a very simple equation, d squared xi by dr square plus 1 by r d xi by dr minus xi divided by r square equal to minus q r by d. This can be in compact form, it can be arranged in this way, d by dr bracket 1 by r d by dr r into xi equal to minus q r by b. So, this is the compact form of this equation that we have obtained, where you can note that xi is nothing but dw by dr. Okay. The equation involving w instead of slope xi can also be written. So, you can see that equation was second order equation with slope, now it will be third order equation. So, shear involves third order derivative. So, it is coming. So, physically we are getting that we are approaching in the right direction. So, d cube w by dr cube plus 1 by r d square w by dr square minus 1 by r square dw by dr equal to minus q r by d. So, this can be written in this form, that again involving the deflection, it can be written in the compact form with this only consist of this 3 terms, that is dw by dr and d by r and d by r. So, you can see here that w is here inside this bracket, that is it is jacketed by so many variables. So, this is a very convenient form. When the q r is known in terms of r, then you can integrate successively and find out, extract the value of w. Okay. Now, let us take the first of the equation 23. So, 23 equation, let us see 23. So, this equation let us take first of the equation, this equation we take. So, if we take the first of the equation of 23, then we know this equation is the first equation, and q into r, actually it will be a total force, total shear force that is acting after integration with respect to 0 to r. So, q into r, that means you can see that q r is the radial shear per unit length. So, multiplied by the circumference of this circular ring 2 pi r, we will get this shear force along this circumference, total shear force. So, this is equal to minus 2 pi integration 0 to r q r dr. Okay. So, multiplying both sides of the equation 24 is this equation by r, and making use of equation 25, we can write this now in this form. Okay. Now, actually my intention is to remove the term q and write it in terms of load small q. Okay. So, we have written like that now. So, differentiate both sides with respect to r. So, I have differentiated both sides with respect to r, that means d by dr, a additional term is here, and here again d by dr, this term is there. Okay. Now, interchanging the integration and differentiation, we now write in this form 1 by d dqr. Okay. So, after integration and dividing throughout by r, we finally arrive at the differential equation of the circular plate under axisymmetrical bending as this. Okay. Now, you can note the difference between these two equations 24 and 25. 24 also involves W, but it is a third order differential equation, and the order of differential equation is less, that means constant of integration will be also less. So, this q r is the shear force, and here you are getting that this is a fourth order differential equation, and small q is the loading, that is distributed loading on the plate. So, both the equation can be used depending on this situation. So, it will be demonstrated through different examples in classes, in subsequent classes. So, today whatever I discussed, the transformation of governing differential equation of the bending of plate from Cartesian coordinate system to polar coordinate system, the expression for stress resultant in polar coordinate system is discussed here. So, that is first using the calculus only I transform the Cartesian plate equation in Cartesian system to a plate equation in polar coordinate system. So, it is transformed actually from Cartesian system to polar coordinate system. Now, the use of polar coordinate system is shown in case of circular plate using a axisymmetrical condition, that is having a rotational symmetry in the plate in respect of loading in respect of S condition. So, with that condition we have seen that the plate equation is now decomposed into a ordinary differential equation, and we have found two types of differential equation to be used for solving the plate problem. One is the fourth order equation, in which the equation this W is related, the fourth order derivative is related to the distributed loading. In another case, we have seen that it is a third order equation, and third order differential equation is ultimately related to the shearing force on the plate. So, two equations are there now. There we derive the two equation in the two forms, and each form has its own advantage and disadvantage. So, depending on the situation and the problem that will be encountered, we can use any of these two equations. Okay. So, today I finish up to this the different applications of the circular plate under axisymmetrical bending will be considered in the subsequent classes. Okay. Thank you very much.